Recall in part 2 that we drew a cartoon of the molecular D2 and the D2 star intermediate probabilities. We now add the helium distribution and sketch the orbits of the deuterons in each case. Then we add the electron distribution starting with molecular D2 and then the intermediate at the average deuterium separation of about 0.1 angstrom. And then we add a much narrower electron distribution for when the deuterons tunnel to the nuclear scale. And draw in the representative orbits of the electrons. And finally, we ask what the electrons look like after the fusion of deuterium to helium. We will, of course, need to describe the electron after fusion of the deuterons. To do this, we will need a complete description of the time-dependent quantum mechanics. We will need to describe quantitatively 3 basic quantum principles. Number 1, the wave functions and energy level of the deuterons and electrons in the intermediate state, then the wave functions and energies of the helium and electron in the final state, and show that the energy change is equal between the starting and final states. Then 2, we need to find the coupling energy between the deuteron and the helium states, then the coupling energy of the electron, intermediate and final states, and show that they are equal. And finally 3, we'll need to describe the time dependence of helium formation and show that it is the same as the electron final state formation rate. Before presenting anything quantitative, we will present an intuitive illustration of how these calculations are made. We will start simple and show how the basic form of the calculation is fairly simple. It's just the complex potential environment that muddies the waters. Fortunately, the computer is fine with complexity. We start with a particle in a box with a ground state of 1/2 a sine wave. This is the wave function which, when squared, gives the probability of finding the particle. The classical representation looks something like this, with the particle going back and forth. You can think of the particle path as 0 to L and back, which would give 1 full wavelength. The wave function of this second energy level then looks like this, with 1/2 the wavelength of the ground state. Keep in mind the mess of particles and the states to be described, and try to think of the particles' potentials as oddly shaped boxes. We need to find the time-dependent behavior of our particles, and thus also draw in the time-dependent part of the wave function. This is just a depiction of the imaginary part of the time-dependent wave function. Note that 1 full wavelength of the time-dependent wave function coincides with the classic time for the particle to go from A to B and back, the same as the full position wave function. This is a general property of typical spatial wave functions and their associated time-dependent wave functions. We can make the same illustration of the second energy level as shown, with the time also having 1/2 the wavelength of the ground state, same as the spatial wave function. We can now show how the probability of finding a particle moves from one place to another. The first and second wave functions may be added together, as shown here, and next, the square of the sum gives most of the probability to the left, as shown. This isn't exactly the way the math is done, but it is the general idea. After some time, the probability will shift to the right, something like this, and then back again. The next illustration shows an intermediate time, which shows how the probability shifts gradually from one side to another. Now we need to look at how changes in the potential change the look and behavior of the probabilities. First, a step increase in potential just below the particle's energy in the middle is shown. Note that this just suppresses the probability in the middle, as you'd expect. Pushing the potential above the particle energy suppresses the probability even more, and a higher potential still requires substantial tunneling, giving 2 very similar probabilities. If these individual boxes were isolated, the probabilities wouldn't change much. We can also draw the wave function of the second energy level as shown, and when squared, this will give essentially the same result as the first energy level. The energy difference would be very, very small, and this is the same phenomena that causes conduction band electrons to have very closely spaced energies in a repeating crystal. We can add the first and second wave functions and put all of the probability in one box. Over time, the probabilities will all flow to the other side as shown and oscillate back and forth. Next is shown a potential box with a small deep hole to the left. The first energy level is inside the hole, and the second energy level shows a small bump over the hole, but mostly above the higher potential. These two could be added together to create all the probability to the right. And the next potential is very similar, but with a barrier between the two boxes. The two energy levels would look similar as before, just less probability in the deep hole for the second energy level. One way to think of this is the deeper potential creates a higher kinetic energy in that region, which will penetrate the barrier faster than the lower kinetic energy on the right. An equilibrium is established with the rate higher moving to the right than to the left. When the two energy levels are added to put all the probability to the right and allowed to oscillate, only a small quantity of probability will oscillate each time constant, leaving most of the probability to the right. Adding one more potential box with a barrier gives a cartoonish look at the potential for deuterium found in the cold fusion reaction. We can place three energy levels on the potential as shown. The far right potential represents molecular D2. The center potential would represent the D2 star intermediate state, and the ground state in the deep well to the left would be the nuclear state of He4. As before, a linear combination of these states would start with all the probability in the far right box to simulate starting with molecular D2. As time moved on, probability would oscillate slowly to the nuclear potential. If this were the whole story, the result would be hot fusion products. Another cartoonish but more appropriate potential might look like this. And with energy loss, the probability would slowly leak out of the D2 area into the nuclear potential, as shown in this cartoon. The time evolution of the deuterons can be calculated from these principles, and remember that the deuteron potential is made up of mostly two parts, the Coulomb repulsion plus the electron energy. Obviously, the deuterons and the electrons are coupled. Next, we take a look at the electron wave functions and see how they evolve from state to state. Start with a molecular D2 wave function, which looks a lot like this at the equilibrium deuteron separation of 0.1 angstroms. The electron follows the deuterons, so when the deuterons tunnel to 0.1 angstrom, the molecular D2 wave function looks something like this, which is closer to the helium-1s orbit than the hydrogen orbits. Now we draw in the D2 star intermediate wave function at the equilibrium separation of about 0.1 angstrom. Shown in red is the overlap of the wave function. There is no need for tunneling here, and the transition is much, much faster than the deuteron transitions. Next, we draw the D2 star intermediate z-axis electron wave function for the deuterons, tunneled to about 4 Fermi, or a nuclear diameter. Again, we do this because the electron and deuterons are coupled. The question is, what is the final electron state? First, we draw in the D2 star electron wave function again, and later we will develop the calculation logic to give the final electron state. For now, we just give it as a spherically symmetric Gaussian distribution of electron probability with energy of about a positive 3,000 electron volts. This distribution will of course spread rapidly as it is not a stationary state, but made up of high energy momentum states from the palladium crystal. The overlap of the D2 star intermediate and final states is quite good and not rate limiting. We haven't answered our 3 questions quantum criteria yet, but are well on the path to understanding the answers. Next time we will discover the critical role of the conduction band electrons in allowing the formation of the D2 star intermediate and supplying the electrons for the fusion energy loss.